So what other bifurcations are there? So we had a settlement bifurcation, which we figured we should expect to show up if there's any bifurcation, and we know of no other, there's no other special condition that happens. So one very common other bifurcation is a transcritical bifurcation. It occurs if for some reason there is a solution, a fixed point solution that exists for all values of the control parameter. So we might as well say, to model this, that x equals 0 is a solution for all values of mu. And so that means for our model x dot equals f of x and mu, that f of 0 and mu is equal to 0 for all mu. Right, so then that is a fixed point for all values of mu. So let's see what happens in that case to our Taylor expansion, and what kind of evolution equation do we get in that case. So we have f of x and mu is given by f of 0 and 0. Again, we're assuming the fixed point is at 0 that we're talking about, plus Taylor expansion df by dx times x plus df by d mu times mu plus 1/2 d2f by dx squared times x squared plus d2f by dx and d mu times x mu plus 1/2 df by dx squared, no, not x squared, mu squared plus higher order terms. Okay, so which terms disappear here? Well, as before, we are at a fixed point, so this term is not there. Then we also assume that x equals 0 and mu equals 0 is a bifurcation. So this term, which again is always evaluated, x equals 0 and mu equals 0, vanishes. And now, how about the others? Well, if f of 0 vanishes for all values of mu, then we also have to have that the derivative of f with respect to mu must be 0 whenever x is 0, because f is 0 for all values of mu if x is 0. So that means that we also have actually this guy is 0, and the second derivative is 0 as well. So then we can, again, we could solve for x if we feel like it, but let me now write down the equation of the evolution equation we get in the vicinity of that bifurcation point. We get x dot equals, there's a term with x mu, so let me call it a times x mu plus 1/2 e x squared, and then there are plus higher order terms. So that's the general equation we expect if there is a fixed point for all values of mu, the same fixed point. So what do the bifurcations look like in that case? Or what does this bifurcation look like? Well, let me draw our standard diagram. So let's take the axes mu and x like that. And so in this case, we have, for all values of mu, we have a solution x equals 0. And we have another solution. So let's write down the two solutions that we have. X equals 0. And the other solution is equal to minus 2a over b times mu. A over b times mu, yes. So we need to again assume something about the signs of a and b. So let's say a is positive, b is positive. Then in that case, if a and b are both positive, then if mu is positive, x would be negative, and we have that other branch looks like this. And if we look also at a case a positive but b negative, in that case we have x equals 0, again a solution. And now a and b have opposite signs, and now if mu is positive, the whole thing is positive, and we get a branch that looks like this. Let's quickly do the stability. So how can we do that? Well, let's consider in our first case, let's assume the A and B are both positive. So if A and B are both positive, let's assume mu is positive, then the right-hand side is positive. Or in other words, we have, if x is positive, mu is positive, we have x dot positive, and everything else looks like this, meaning the stability looks like that. So this guy is stable, as is this guy, whereas this guy is unstable, as is this guy. Let's just complete the picture so we can talk about it in one fell swoop. So stability, in this case, when A and B have opposite signs, in that case, if mu is positive, let's say mu is negative, A is positive, X is positive, then this would be, this term would be, no, you don't want to draw, excuse me. If X is positive and mu is negative and A is positive, this is negative. B is negative and X, so these both would be negative. So up here, the flow is downward. And then the rest looks like this. With stability, this branch is again stable. And this guy is stable, whereas these are unstable. Okay, good. So of course you could do the other two cases analogously, but let me not do that right now. So what do we see? Well, you could be surprised first because we expected, or from what we saw so far, when we get to a bifurcation point, that's a point where the implicit function theorem doesn't apply, and therefore we are not guaranteed a unique continuous branch. And so previously that meant that solutions either appeared or disappeared. But here, no solution appears or disappears. We simply have two solutions before the bifurcation and two solutions after the bifurcation. So what's the point? What's the thing about this bifurcation? Well, remember, the implicit function theorem doesn't just talk about a branch existing, but actually a unique branch existing. And so it's the uniqueness that's not the case here, right? You have, if you follow, say, the stable branch here and increase mu, at the bifurcation point, the continuation for positive mu is not unique. You could either stay on x equals 0 or you could go into this other branch. So in this case, it's not unique. The branch is not unique. And that's what characterizes that bifurcation. The other thing that's characteristic for that bifurcation is that the stability of the two branches exchanges. So below the bifurcation point, the x equals 0 is stable, and above it's the other branch. Here, for the other parameters, it's again the x equals 0 being stable below the bifurcation and the other one above the bifurcation. If you switch the signs around completely, the stabilities will also switch around. But in all cases, what you would have is what's called exchange of stability. That the stability goes over from one branch to the other. There's also another feature I want to mention here, which is the following. You see here, this branch, x equals 0, is linearly stable. And so if you start in this wedge here, and the solution would approach that fixed point. Good. However, you notice that if you make a perturbation that's not very small, like, if you make a perturbation that's large enough that actually gets you above that line, then the perturbation will actually grow and the solution will go someplace else, which is completely unknown in this model where it would go. But so in that sense, this system is excitable, so to speak, that if you have a perturbation that's very small, nothing happens. Well, nothing as in the solution comes back to that fixed point. But if the perturbation is larger, you actually go to another state or something. Let me mention one example that you're familiar with, although you may not have recognized it as a transcritical bifurcation, which is the logistic equation. Of course, you have seen the logistic equation in terms of for population growth a long time ago, beginning differential equations. So you have the equation dn by dt, where n is the population size, is like an, so you have exponential growth. Each individuum propagates or reproduces with a certain rate, and so the whole population grows proportional to the population size. But there's competition between the individuals, and so the population growth saturates. There's a finite carrying capacity, and you have this minus n squared term. And you see that, of course, is exactly the same form as what we have up here for our transcritical bifurcation. So why did this equation never show up in terms of a bifurcation? Why doesn't one think about bifurcations there? Well, it's a very simple reason, is because, I mean, the bifurcation diagram, we can actually look at the bifurcation diagram they have here. It would be this one. Looks like this. And so you could ask, well, what about this branch? There's a stable branch here, which we never talked about. We only talked about this one. Well, it's because here, this is where the other solution here would be a negative population. And so this whole range here was just never considered for that equation. But in principle, mathematically, the logistic equation exhibits the transcritical bifurcation if you allow A to be negative and maybe the population to be negative. I think in another video, I will talk about some more interesting examples for different bifurcations, but not right here. Right now, let's just leave it at that we have, if there's a solution that exists for all values of the control parameter, the same solution, then if there's a bifurcation, we should expect a transcritical bifurcation, which has this form.